Okay, let's dive in. We're exploring something truly incredible today.
Mm.
The immense energy hidden inside atoms.
Right, that nuclear energy. And specifically, the two main ways we talk about getting it out, fission and fusion.
Exactly. We've gone through the articles and notes you sent over, really trying to get a handle on them.
Yeah, we look at how these processes work, what the sources are saying about using them for, actual power generation, and the bigger picture.
So our mission here is basically to unpack all that material together. We want to pull out the key ideas, really understand the mechanics of fission and fusion,
Uh-huh. See how they're used, or, well, hoped to be used for energy.
and weigh the pros and cons that are mentioned in the sources. Just give you a clear picture without getting totally bogged down in the deep
That
physics.
sounds good. So, to set the stage, based on what you provided, the core idea is simple. Atomic nuclei pack a huge energy punch.
A really staggering amount. And the sources lay out these two main methods to unlock it. Nuclear fission.
And nuclear fusion,
Right.
almost like opposites in how they approach it.
Yeah, exactly. Let's tackle fission first. What do the sources say it actually is?
Well, fission, according to the material, is all about splitting. Taking a big, unstable nucleus, the classic example is always uranium-235,
Okay, big and unstable.
and breaking it apart into two smaller daughter nuclei, as they call them.
Right. And how does that splitting start? The sources say it's triggered.
Yeah, it happens when that nucleus, the U-235, absorbs a neutron. That absorption kind of tips it over the edge.
Makes it even more unstable.
Exactly. For a fraction of a second, it becomes U-236, and then, boom, it squits.
Okay, absorbs a neutron, becomes unstable, splits. And the sources say when it splits, it releases,
Right.
well, obviously the smaller nuclei.
Yes, the daughter nuclei, but also, and this is key, it kicks out 2 or 3 more neutrons.
Ah, more neutrons.
And a whole lot of energy, a significant burst.
Right, and those extra neutrons. This is where the chain reaction thing comes in, isn't it?
Precisely. Those newly released neutrons can zoom off and hit other nearby uranium nuclei.
Causing them to split too.
You got it. Which releases more neutrons, hitting more nuclei. It cascades. That's the chain reaction the sources describe.
Okay, I can see how that could, escalate very quickly. The sources are clear that an uncontrolled reaction is basically an atomic bomb.
Absolutely. So
Yeah.
for power generation, controlling that reaction is everything. Has to be steady, managed.
Makes sense. And the sources detail how reactors do that, right? The different components.
Yeah, they break down the key parts. First, you've got the nuclear fuel itself.
Yeah.
Usually uranium or plutonium isotopes.
Held in rods, I think.
Yes, fuel rods. That's the stuff that's actually splitting.
Okay, that's the source. But you mentioned the neutrons released are fast, too fast.
Right. The sources say they need slowing down. Slower neutrons are actually more likely to be absorbed by another U-235 nucleus and cause fission.
So you need something to slow them down. That's the moderator.
Exactly. Often graphite or sometimes heavy water.
Yeah.
Its job is just to reduce the speed of those neutrons, make them more effective.
Got it. Moderator slows them down.
Right.
But you still need to control the rate of the reaction, like how fast it's all happening.
And that's where the control rods come in, according to the materials.
Right, control rods made of stuff that absorbs neutrons, like cadmium or boron.
Yeah, materials that just soak neutrons up. By lowering these rods into the reactor core, you absorb more neutrons, slowing the chain reaction down.
And if you raise them, fewer neutrons get absorbed, and the reaction speeds up.
It's basically the reactor's accelerator and brake pedal, all in one, fine-tuning the power level.
Okay. Then there's the heat. All this splitting generates enormous heat.
Immense heat. So you need a coolant, a liquid or gas that flows through the core, absorbs that heat, and carries it away.
Transfers the thermal energy somewhere else.
Right. And finally, there's the shielding. The sources really emphasize this.
Because the leftover bits, the daughter nuclei, are radioactive.
Highly radioactive. Things like barium, krypton. Very hazardous stuff mentioned in one source. So you need a thick concrete shield around the whole thing.
Containment, to keep the radiation in and protect people and the environment.
That's the idea. Fuel splitting, moderator slowing neutrons, control rods managing the rate, coolant removing heat, shield containing the radiation.
And the heat from the coolant, that's what makes the electricity.
Yeah, the basic principle is simple then. The hot coolant boils water,
Creates steam,
which turns turbines,
which spin generators.
and you get electricity. It's a nuclear-powered steam engine, essentially.
Okay. Now, the sources definitely present this as a technology with, well, two sides to the coin, advantages and disadvantages.
Definitely. They lay out a pretty balanced perspective, it seems. Let's look at the pros first.
Sure. Big one mentioned often, No polluting gases during operation. No CO2.
Right. Doesn't contribute to climate change in its direct power generation phase. That's a major plus.
And it's reliable, isn't it? Runs day and night, whatever the weather.
Very reliable. Provides that constant baseload power that grids need, unlike, say, solar or wind, which fluctuate.
The energy density also sounds incredible.
Phenomenal. A tiny bit of uranium produces a huge amount of energy compared to coal or gas.
And the sources connect that to needing less mining, less transport, fewer of those kinds of environmental impacts.
True. Lower fuel quantity needed. And once the plant's built, the sources say the fuel cost itself is actually pretty low for the power you get out.
There's also a point about the high-tech nature maybe benefiting other industries.
Yeah, spin-off technologies. Plus, these plants are built to last a very long time. Decades.
Okay, but then there are the downsides, and they seem pretty significant according to the sources.
Oh yeah, the big one everyone talks about, radioactive waste.
The stuff left over after fission. The sources say it's dangerous for thousands of years.
Or much longer. Hundreds of thousands even. And figuring out how to store it safely, securely, for that long. It's a massive, expensive challenge. One source really hit home the scale of this problem globally.
That's a really long time to guarantee safety.
It really is. Then there's thermal pollution. The hot water release can affect rivers or oceans nearby.
Local ecosystems.
Right. And then the big fear, accidents. They're rare, thankfully, but the sources point to Chernobyl, Fukushima.
Yeah, those show the potential for catastrophe if things go badly wrong.
And those accidents definitely fuel the negative public perception that's often mentioned as another hurdle. People are understandably wary.
The cost, too. Building these plants is incredibly expensive.
Hugely expensive upfront. And, importantly, the cost of safely decommissioning them at the end of their life is also very high. That's often overlooked.
And one last point from the sources, they can't really ramp up and down quickly.
No, they're not great for responding to sudden peaks or drops in electricity demand. They like to run steady.
Okay, so that's fission, splitting heavy atoms, controlled chain reaction currently used, low carbon power, but serious waste and safety concerns.
Fair summary based on the material. Now let's switch gears completely. Nuclear fusion.
Fusion. The sources say this is basically the opposite process.
Exactly. Instead of splitting big things, you're joining small, light nuclei together.
Like hydrogen isotopes, deuterium, tritium, things like that.
Precisely. Smashing them together so hard, they fuse to form a slightly larger nucleus, usually helium.
And this is what happens in stars, like our sun.
Yep. The sources are clear. This is the sun's power source. Constant fusion reactions happening in its core.
Wow. And it also releases energy.
A tremendous amount of energy. The sources actually highlight that gram for gram. Fusion releases even more energy than fission.
More? How does that work? Where does the extra energy come from?
It's that Einstein equation, EMC arc. When the light nuclei fuse, the resulting heavier nucleus actually has slightly less mass than the original two combined.
So some mass just disappeared?
It's converted. That tiny amount of missing mass transforms directly into a huge amount of energy.
Okay, wait. If it releases more energy and the sources suggest it might be cleaner, why aren't we using fusion power everywhere? What's the catch?
The billion-dollar question, or maybe trillion-dollar question. The catch is, it's unbelievably hard to do on Earth.
Harder than fission.
Orders of magnitude harder, based on the physics described. Think about nuclei. They have protons, right? Positively charged.
Right. And positive charges repel each other, like trying to push the north poles of two strong magnets together.
Exactly. That electrostatic repulsion is incredibly strong at nuclear distances. To overcome it, to force those nuclei close enough to actually fuse.
You need something extreme.
Extreme is the word. You need absolutely mind-boggling temperatures and pressures, like conditions similar to the core of the sun.
But we can't just recreate the sun's core in a building.
Well, we kind of have to try. The sources mention needing temperatures between 100 and 200 million degrees Celsius in a reactor here on Earth, even at achievable pressures.
100.
Yeah.
That's insane. Hotter than the sun itself, isn't it?
Much hotter, yeah. Creating and just containing plasma at those temperatures is an immense scientific and engineering challenge.
So keeping it stable, getting more energy out than you put in to heat it, that's the hurdle.
That's the core problem. The sources mention experiments, like JGT in the UK, have achieved fusion reactions for brief moments.
Right, I saw that mentioned. Proof of concept.
Yeah, but getting to a point where it's sustained, produces net energy gain, and is commercially viable, we're not there yet. Still very much in the research and development phase.
Okay. And what about the byproducts? The sources seemed more optimistic here compared to fission.
They do. The main product is helium, which is harmless. And crucially, fusion doesn't produce the long-lived, high-level radioactive waste that fission does.
So less of a waste disposal nightmare.
Potentially, yeah, much less. And also, the physics of it makes a runaway chain reaction and meltdown impossible.
Hmm.
If you lose containment, the reaction just stops.
So inherently safer in that respect, if we could get it working.
That's the potential advantage, yes. Safer operation, less problematic waste.
Okay, so let's just quickly recap the comparison based on the sources. Fission versus fusion.
Right, nuclei involved. Fission uses big, heavy ones like uranium.
Fusion uses small, light ones like hydrogen.
Process. Fission is splitting apart.
Fusion is joining together.
Energy release. Both huge, but fusion releases even more per unit mass.
Chain reaction. Fission relies on one.
Fusion doesn't have one.
Products. Fission creates nasty radioactive waste.
Fusion mainly creates helium, much less hazardous waste.
Control. Fission is controlled now in reactors.
Fusion control for power generation is still the major challenge we're trying to crack.
Natural occurrence. Fission isn't really natural on Earth.
Fusion is what powers the stars, naturally occurring on a massive scale.
Safety. Fission has waste risks and meltdown potential.
Fusion, hard to start, but potentially safer, no meltdown risk like fission, less waste.
And current use. Fission is here and now, providing electricity.
Fusion is still experimental, future tech, hopefully.
Okay, so pulling all this together from the sources,
Yeah.
what does this mean for you, the listener?
Well, it means you've now got, hopefully, a clearer grasp of the basic physics. Fission splitting, fusion joining.
Can you see the very different engineering worlds they inhabit, the different safety questions, the economics?
You've got fission as a current reality. Reliable, low-carbon electricity during operation.
But with that undeniable long-term radioactive waste problem and the shadow of potential accidents,
And then you have fusion, the dream, really, mirroring the sun's power,
offering immense energy, potentially cleaner.
but facing these almost science fiction level challenges of heat and pressure before it can become practical.
So two very different paths for nuclear energy laid out in the material we looked at.
Yeah, one path we're already on, with known bumps and potholes, and another path that's still mostly under construction, but promises a potentially smoother ride way down the line.
Right. So maybe a final thought to leave you with, drawing from all this.
Considering everything we've unpacked from the sources.
Given the very real and difficult challenges of managing fission's radioactive legacy,
And the absolutely huge technological hurdles still facing practical fusion power.
which approach seems more promising for our long-term energy future? Is it one or the other?
Or perhaps the answer lies somewhere in between. Maybe it's about carefully using the fission technology we have now while really pushing hard, investing relentlessly in making that fusion dream a reality. Something to think about.